On behalf of the Center, I'd like to welcome Father David Brown to be our lecturer today. By way of introduction, I'm Michael Rogers. I'm a fellow here in the Center. Father David Brown is a researcher at the Vatican Observatory, where he's also served as dean of their summer program and currently serves as the curator of the telescopes at the Roman branch of the observatory. He earned his PhD from Oxford in 2009 and has published extensively on binary population synthesis as it refers to subdwarfs, metallici, and UV excess in elliptical galaxies. Beyond his main academic work, he's also written on the theological implications of scientific theory, the Higgs boson, and the necessity of the Vatican Observatory. His research interests include stellar evolution, stellar population synthesis, binary population synthesis, evolution of hot subdwarf stars, multiple populations in global clusters, N-body stimulations of global clusters, globular clusters, binary evolution, and Roche lobe overflow, contact binaries, stellar modeling, horizontal branch stars, helium stars, and open clusters. And I will pretend to know nothing about any of those things. On a personal note, I had the great pleasure of meeting Father Brown in Rome and having many conversations with him while we were there during my own studies. And I've always been impressed with his work and the manner in which he links his life as a scientist to his deep faith. And so it's my great pleasure to introduce Father Brown.
Thank you very much, Father Rogers. It's a great pleasure. I guess I better turn this thing on, right? It's almost like Mass. And the great challenge is to know when to turn it off as well. Anyway, it's a great pleasure to be here before you today, here at Holy Cross, just presenting on this topic right over here, which is very dear to me because it's a huge part of my life. And so right over here, the subject is basically Catholicism and science, mainly astronomy. It'll be overwhelmingly directed towards from that angle right there. A new rapprochement, sort of in the dialogue between faith and science, right over here. So a little outline of the talk. I'll show you where I work, what I do, what lies before us, what confronts us, new discoveries, final frontier, and what that says about what it says about our faith. Sort of the interaction, sort of the dialogue that happens. What are the general principles that go into that form sort of this dynamic sort of interplay between science and faith, and of course just some final thoughts. First of all, where I work. So the Vatican Observatory, although those are not my current offices or dwellings right there. That was the original observatory in Rome, which was founded in the year 1582 by Pope Gregory XIII, with the purpose of reforming the old Julian calendar, which was off by a couple of days by the time they got to the 1500s after more than 1,000 years having been used. And of course, they needed to know the dates for Easter and, of course, a lot of high holy days in order to have a well-running church and all these things. So the Pope convened a lot of the astronomers that were already part of the papal court. They had been there long before. And then their purpose and their first work, that institutional beginning of the observatory, was the reformation of the calendar, that calendar that we still use today. So right over here, that top picture right over there is actually a part of what's now called the Vatican Museum, but that's actually a part that is not usually accessible to the public. And these are the various spaces inside. You have a solar clock and all these things. You needed a knowledge of astronomy to be able to reform the calendar, to be able to tell time right over here. The observatory originally was located, all those spaces were right there, that big long building right over here, that's now the Vatican Museum. And that top part right over there is the Tower of the Winds, which is where all those rooms in that previous slide were located. Later on, it was moved to the top of the Roman College, of which you see a picture right over there. That was the original Jesuit university, built in the early 1550s, with its church, its campus chapel attached directly behind it, the Church of Sant'Ignazio right over here, and the domes would have been on the very top of the church and of the college as well. The observatory was confiscated in the year 1870, approximately, by the government, and so it had to be refunded once again. And so Pope Leo XIII is the one who did that. And the new telescopes were put directly in what is now left of, what is now the Vatican right over here. You can see some of the domes along the back wall right over there. 1, 2, 3, right there. The telescope's there. But then, because of light pollution, we had to leave central Rome in the year 1930 and then make our way out from Rome, which is all the way up there, where you see Città del Vaticano and then Roma, and then make our way right over here to a location that's about maybe 25 kilometers, about 17 miles outside of the city. It was much darker at the time. Moving right next to that lake right over there, Lake Albano, which is actually a crater lake. So it's a volcano. And you see right over here, that's the front of the building. That is the Pope's summer palace. The popes normally go there for about 4 months out of the year to spend the summer. Originally, it was the only way to beat the heat in ancient times. You just leave Rome to an area that's higher in elevation, next to a lake, and then about 10 degrees cooler. So that's the papal summer palace. And then on the roof of that palace, which you can see right over here, you can see the palace right over here. This is looking from the lake. See right over here, you can see 2 of the domes. And then if you're on the roof, that's your view right up there with one of the domes in your sight right there. So this is sort of the Camp David of the Pope, if you want to put it that way, just to use an analogy that we're accustomed to here in the U.S. You go inside the palace, and that's an inner courtyard right over here. You see one of the domes there. That's the telescope in there. But of course, we have a new telescope as well. In fact, our modern telescope is actually not in Rome. It's actually outside of Tucson, Arizona. Why? Because in the 1990s, when it came time to build a new telescope, because the old ones that we had, though they work well, by this time were technologically obsolete, we got permission from the Vatican to build a new telescope. You need modern instruments to do modern science. That permission was given, and of course, the question that arose naturally once we began thinking about those things was, well, do we build the scope here? The answer was no, because Rome has grown a lot in the last 100 years. The suburbs are we are now the suburbs of Rome. And because of that, you have light pollution, and that it's the one thing you cannot have. You need dark skies. Hence, the desert in Arizona. You go out a couple of hours from Tucson and then up a mountain that's called Mount Graham, 11,500 feet, and there you find our telescope as well, right there. That's one picture of it. A couple more pictures right there. These are the 2 scopes on top of the Papal Summer Palace. And then our telescope in Tucson, Arizona. Our telescope is not the only one up there. There are 2 others that belong to different countries. This is the dome, exterior dome of our telescope right there. This is just some of the life of astronomy right there in both Tucson and in Rome. So once again, the modern scope, its dome, and that's me with an older telescope in Rome as well. It's a nice thing to be able to use. A couple of pictures of past times right over here. You can see the popes just looking through the scope. That Pope Paul VI in the 60s just addressing mission control, and through mission control speaking to the first man who had landed on the first moon landing by people from this world. Okay. Anyway, so other visits by popes. Pope Benedict came to bless the new hut that we moved into just a few years ago. That's a picture of him holding our Mars meteorite. Brother Guy Consolmagno, right over here at that time, would have been the curator of the meteorites. He's now my boss, the director of the observatory. That's him showing Pope Francis, the same thing right over here. And that's in the library. We also have a number of very precious old books on that. So I was given the responsibility of showing Pope Benedict some of these books. It was really a nice thing. Anyway, what I do. So my field of specialization is called stellar revolution. Once again, the observatory. Let me explain what it is. It's a real, fully functioning astronomical observatory, scientific institution like any other astronomical observatory. And the main function of such an entity is to do research in astronomy, in astrophysics, by astronomers, by astrophysicists. There are 16 of us, roughly, who work in the house. Half of us in Rome, half of us in Arizona, especially those who use the telescopes a lot. Most of us who work there as part of the observatory are members of the Society of Jesus, Jesuits. Why? The observatory itself is a direct work of the Holy See. It does not belong to the society, but it was entrusted to the society. That means that we provide most of the personnel for the observatory. So we're all either priests or brothers, and also scientists as well. Each one of us having a different field of specialization. Some are cosmologists, in which case you study the universe as a whole, things like the Big Bang, possibilities of other universes, right, a multiverse. Others study galaxy evolution. How did the galaxies form, their structure and all those things. Others, and in fact, our biggest group are the ones who study, in one way or another, basically space rocks, whether they're meteors, meteorites, asteroids, comets, or planets, including Brother Guy. Then my field is called stellar evolution. So I study stars. A cosmologist really does not have to understand how stars work in great detail, because for him, his basic building block, the smallest thing that he studies, is a galaxy. How galaxies cluster, the large-scale structure of the universe, how they cluster in groups of thousands or tens of thousands. So of course, if your smallest unit is a galaxy, most of the time you don't have to worry about what's in a galaxy, but we know there's usually between 100 billion to 1 trillion stars in a galaxy, and that's important, and of course we're in there as well. So my job is to study stars individually, stars like the sun, or perhaps in small collections like clusters, open clusters like the Pleiades, or globular clusters, stars of about 1 million stars together, certain parts of our galaxy, and of course stars in other galaxies. That's the Andromeda galaxy. That's the galaxy that's closest to us, to the Milky Way. Anyway, so I can tell you basically about how stars are formed, how they evolve, and ultimately what their fate might be. Are they going to die a quiet death, in which case they're called white dwarfs? They just flicker out after they run out of fuel. Or if they're more massive, they'll usually blow up in what's called a supernova, and the remnant of that will usually be a very compact object, either a neutron star, a thimbleful of which will weigh several billion tons, or, in a more extreme case, a black hole. An object so massive that it's collapsed under its own weight, its own gravity, like that. And so this tells you, basically, how stars evolve. This is basically, maybe it's a clearer diagram right over here. So a star, like the sun, will have this type of evolution right over here. It'll become a red giant in about 5 billion years. Then it'll start shedding its outer layers and form what's called a planetary nebula, and ultimately wind up as a white dwarf. It will not go beyond that point because it does not have the mass and therefore the gravity to keep contracting its center, to keep fusion reactions going. So finally you get to iron, and then you get a supernova. So the sun will never blow up. Okay? So you don't have to worry about that. But you will have to worry about this. Long before it can ever blow up, well, it'll never blow up, because if it did, it'd be just a couple million years. We wouldn't have lived already. We'd already be dead. But because it's the bigger stars, the more massive stars that blow up, but they only live a couple of million years. They burn their fuel at a very fast and furious rates, and they only live a couple of million years before they go supernova and all that. Whereas the smaller stars, lower mass stars like the sun, burn their fuel, their hydrogen, and then other fuels such as helium, very slowly over billions of years. But we do have to worry, because when the sun gets to this stage, to its red giant stage in about 5 billion years, its outer surface will expand and, of course, engulf the planet Earth. So by then, we will have found another home. We have 5 billion years to solve that problem. Anyway, the one point to make right over here is that the mass of the star is the most important property of the star. The mass of the star is what, first and foremost, will determine what kind of death, what kind of fate it will have, right over here. So only the massive stars, the most massive ones, blow up in a supernova and give you black holes or neutron stars right there. So this is, I'll just explain this right over here. If you make a plot, a graph of the brightness of a star, vertical axis, and its temperature, they fall in these kind of patterns right over here. This is called the Hertzsprung-Russell diagram. And that's a way of allowing us to know the particular history of a cluster of stars. So over here you see the more massive ones, the blue ones are up there. The less massive ones are the ones in red in the lower right-hand part, and the sun would be in that part right over there. And then, of course, as they age, they move to different parts in that diagram. So in particular, you look right over here, the sun. As it evolves, we'll trace that kind of path as time goes on. and then go down to what's called a white dwarf right over there. These are actually real pictures right over here. This one here. These are stars just in the local neighborhood of the sun, and their properties measured by a probe called Hipparchus. And so you have this. So just like the theoretical diagram. But in general, what I study are stars in clusters, globular clusters in particular. So if you make a plot of their temperature, whatever you hear, versus their brightness, their luminosity, they look like this. So what happens is that line that you saw right over here, that was going like this, right up there, and right up there, all these stars that were up here basically evolved long ago off that line, blew up, and something else happened to them. Whereas these are the lower mass stars that are still burning, and these are the red giants. And then these stars right over here are horizontal branch stars. These are the types of stars that I study. If you notice right over here, they don't even put that star in this diagram, but it would be basically right in between here and here. And so that would be a helium burning star, horizontal branch star, subdwarf B star. These are all different names with slight variations for the same thing. So these are the kind of stars that I study. So these are what I would call stars in midlife crisis. Okay, so when a star is very young, this is like a star as a teenager. It has a lot of energy, maybe in its early 20s. And then by the time it gets here, maybe it's around 30, using an analogy, human aging, it's getting older right over here. And then it hits midlife crisis. And in midlife crisis, what happens is that suddenly it gets a second burst of wind. And it starts burning once again. Here, a red giant is not burning its fuel at the center because it does not have the gravity and the temperature to fuse what's there in the center, which would be a helium center by the time it gets to that. But suddenly, gravity squeezes it so much that finally you start burning helium at the center. That's what was left over after you burnt all the hydrogen at the center. And so it ignites again, but only for a couple million years. So it tries to recapture a bit of its former splendor. But like middle age, it'll never quite be like when you were much younger. Okay? Anyway, so that's the kind of star that I study. And these are very hot blue stars that you find all over the universe, right over here. So the main question is, how do we get those stars? Those stars are almost entirely made up out of helium, and most of the outer envelope has been stripped away. So the big question in my field of studies is, how did it lose most of its outer envelope? Why is it just the center? What was the mechanism that caused that? And the answer is, we still don't know. But basically, one possibility is that the star will lose most of its outer envelope if it's in a binary system, and another star basically pulls its outer material towards itself. So that's one possibility. So I study binary stars, so that's my real field of study. I study stars that come in twos. And these are all the different possibilities that you get with binary stars, because depending on what the original masses of the stars is, and the separation and all that stuff, you can get different interactions. Anyway, so my own point with regard to this is basically, and what I want you to keep in mind for what follows for the rest of the presentation, is this. First of all, I study these helium-burning stars, these horizontal branch stars. Number one, they're everywhere. They're ubiquitous. You find them in very different populations throughout the universe. You find them in clusters and galaxies. You find them in the disk of the galaxy. You find them in clusters above the galaxies, globular clusters. You find them in other galaxies called elliptical galaxies, blah, blah, blah. And that's a lot of fun because you get to study different things in different environments. Another thing is that because they're found in very old galaxies, these elliptical galaxies, they could potentially be used to give you an age estimate of the universe. That's a possibility. So they have implications for cosmology. So once again, I like things that are connected. I study individual stars, and yet somehow, out of the behavior of these little individual stars, it also has cosmological implications. You could get, potentially, an age estimate for the universe. Another way of finding an age estimate, getting an age estimate like that. I like studying them because you can study them in twos or ones. Okay? How are they produced? How does the environment play a part in which certain stars are found and all these things? So my main point is this: stars lie at the crossroads of the different branches of astrophysics. Everything is interdisciplinary, interconnected. Keep that point in mind. That's what I like it. I like it because you can study them in cosmology and galaxy evolution, even in planets. Planets, which sometimes might be found in orbit around some of these stars. And that gives you a clue as to how the star might have formed as well. Was it a planet that actually interacted with the star? Okay, so anyway, so let's move on to another parts of the talk and move on to basic principles of the faith. So right over here, one of my favorite books, Space is Big. You just won't believe how vastly, hugely, mind-bogglingly big it is. So what are we confronted with when we look out into the heavens, into the cosmos? We are confronted by a lot. Let's go through a tour of the universe very quickly. Let's start with the Earth, our home. It's a big blue marble right over here. A beautiful photograph taken by a satellite orbiting around the Earth right over here. Of course, a nice view of the same planet, our home, from the International Space Station in orbit above us right over here. You can imagine being an astronaut, having to look at that every day. That would be, I would never forget that. Okay. Various space probes sent away on their missions to different parts of the solar system, whether it's Jupiter, Saturn, Pluto. They like to turn these probes around once they've been launched and once they're far outside of Earth orbit. Just turn them around and have them take a picture of the Earth as they leave. So these particular pictures were taken by the Galileo mission, which was on its way to Jupiter. You can see the Earth, and you can see the moon right there. Point of view, looking at us as it left. Our closest neighbor, Mars, right over here. And you know that you have a couple of rovers like Curiosity roaming around the surface of Mars, right? Taking all these wonderful pictures. There's a picture actually caught by Curiosity of the sunset, our sun, setting, and how that looks like on Mars. Not the Earth, but that's Mars. That's the sun setting on Mars. Yeah. The solar system is a huge place. We think it's small by our standards, but it's huge. Right over here. If you were to go in a car at 100 miles an hour, let's say from the sun, or let's say the Earth, it doesn't matter, all the way to the outer orbit of Pluto, let's say, whether you think it's dwarf planet or planet, you know, that debate's still kept alive by some people. How long would it take? It might take you about 5,000 years, meaning that if you hopped into your chariot, assuming it could go at 100 miles an hour during the time of Pharaoh, the time of the pyramids, and you started your journey to the outer part of the solar system, you'd just be getting there right now. The solar system is huge. Let's pan out a little bit more. We have the sun, our solar system in the center. These are the star systems that are closest to us, right? The stars and probably planets around them that constitute our neighborhood, the closest of which is Proxima Centauri. So if someone asks you, what is the star closest to us? You would say Proxima Centauri, but it's actually not a single star system, it's a triple star system. Those are three stars in orbit around one another. Okay? Not just a binary star, but a triple star. Let's pan out a bit more. The galaxy. Let's go over here. Forgot one thing. If you were to go from the sun to Alpha Centauri or Proxima Centauri at light speed on the Falcon with Chewie as your companion, how long would it take? It would take you 4 years. 4 light years is the distance between our system and that system right there. 4 years one way, roughly. Okay, 8 years round trip. If you could go at light speed, which, you know, we're not capable of doing that yet. Probably not for a long time, if ever. The galaxy, where are we? They say that we're here about 20,000 light years from the center of the Milky Way galaxy. By the way, at which they say lies a supermassive black hole. So 28,000 years to get to the galactic center. To go from edge to edge in the galaxy, 100,000 light years, meaning that at light speed it would take you 100,000 years to traverse our galaxy. To go to the nearest galaxy outside of ours, the Andromeda Galaxy, M31, 2 million light years is the distance, meaning that it will take you 2 million years at light speed to get there to the galaxy closest to ours. Oh, we have a lot of time. And we look in every direction and you see galaxies, these island universes. Galaxies which on the order might have anywhere from 100 billion to 1 trillion stars in them. 100 billion, that's 100 times 10 to the 9. And a trillion, that's 10 to the 12, right? A 1 followed by 12 zeros. Which if you were to count a number every second, counting from 1 to a trillion, it would take you what? Some smart Alex always said, it would take you a trillion seconds. But in more normal numbers, what is a trillion seconds? Well, that's 30,000 years. It's a big number. Galaxies in every direction, they say about 100 billion galaxies in the known universe. It's huge. Over here. That's the Hubble Deep Field photograph. They pointed the Hubble to a very small dark patch in the sky, just curious to see what they would get. A plethora of galaxies in every direction, very old galaxies. To look farther back into the universe is also to look farther back in time. So over here, that's a more recent picture taken in 2012, the original in 1995. And then finally, or next to finally, is a diagram obtained by the Sloan Digital Sky Survey, SDSS, which has as its mission to map the known universe. Every point that you see there is no longer a star, it's a galaxy. It's about 500 million galaxies. The parts that are dark are parts that were not covered because of dust in the galaxy that obscured that right there. So that's looking out, basically right over here to that distance right over there. Present is where you see that little point, and then just going out. That outer part right over there, multicolor. Hold on, it's just another diagram right there. This is the afterglow of the Big Bang. Afterglow of the Big Bang. First detected back in the early 1990s, originally by the COBE mission, COBE satellite. And of course, a diagram of the origin of the universe, the Big Bang, okay, and a singularity, and then exploding, and then the universe. Once again, you have the afterglow of the Big Bang, and then our current universe right over here. Then again, they say that all we've ever seen is only about 5% of the known universe. Because everything that we've seen, all the maps that we've made, are based on one thing, the light that we receive from those distant objects, and we form our image of what we think the universe looks like. But then they say, hold on, that's only 4 to 5% of the known universe. The rest of it being mostly in what's called dark energy and dark matter. There's only one problem, we really don't know what they are. We think it's there, or they're there, but we don't know what they are. It is a mysterious, mind-boggling universe. These are just some dark matter simulations right over here in the background right here, with gas and galaxies clustering right there. And then right over here, this is a real picture taken with this kind of blue part right over here. They say it's the effect of dark matter. You're not seeing dark matter, but you're seeing the effect of it. That's what they think. But there's nothing certain about that yet. And then, of course, we add on top of that the possibility that our universe is maybe only one of an infinity of universes that might be out there. We don't know if the multiverse is a reality or not, but that's the speculation on the part of a lot of cosmologists, in particular a lot of string theorists out there, that our universe, we might not be the only ones. There might be other parallel universes that pop into and out of existence right there. Each universe having its own different set of laws and constants, possibly. And then if we go in the opposite direction, what are we confronted by? We saw the macrocosmos, if you want to put it this way. If we go in the opposite direction, the micro, we find an incredible order of particles that atoms made up out of neutrons and protons and electrons. In turn, those protons and neutrons are made up out of smaller things called quarks, even more elementary particles. And then that there are 4 fundamental forces of which we know in this universe, 4 fundamental interactions: gravity, the weak force, electromagnetic force, and a strong force which is responsible for the binding of protons and neutrons in the nucleus. An incredible symmetry in order we find there. And of course, just a few years ago in 2012, the discovery of what had been predicted long ago, the Higgs boson, which the Standard Model thought would be there. And finally, the construction of the Large Hadron Collider in Switzerland inaugurated or allowed that to be the case. They actually found it right over there. So a stunning confirmation of theory right there, the Higgs boson, which is supposed to be a large explanation as to why other particles have mass, a fundamental particle. We also see that fractals, these geometrical sort of patterns stemming from mathematics, can very often be used to model chaotic systems in the universe. So even where you see chaos, there might be an underlying order. Okay? And finally, what else are we confronted with when we look at this? And just in the last 2 or 3 months, it just keeps coming at you. It's wonderful. I love it. I love having my mind blown. Gravity waves, about a month ago, right? Once again, predicted by Einstein's theory of general relativity to be there. It took decades actually to find them, and then finally they were detected at these 2 LIGO detectors, one in Washington State, the other one in Louisiana. A stunning confirmation, once again, of at least that we got our finger on the right thing. The waves themselves are not new, which is something that we predicted, but the fact that we found them was wonderful. It's also an even more monumental discovery because it allows us to detect things out there in the universe, not based on their light. Once again, the problem with dark matter is this. If dark matter is there, the one property about dark matter is this, that it does not emit or absorb electromagnetic radiation, better known as light, right? It's once again, it's a philosophical problem. If you look out into the universe and you see a black patch, there's nothing there, and you conclude that there's nothing there. Not necessarily. It could be the case that that the light from stars has been obstructed by some cloud that absorbs the light. And of course, you could have dark matter there that does not emit light, electromagnetic radiation, but which is there, and its effect could be detected in other ways because if it's mass, it also gravity. And gravity, according to relativity, massive objects can bend light. You have what's called a gravitational lens. You see these distortions of stars and galaxies. You can say, there might be some dark matter there, which is bending light. Anyway, so could this be another way of seeing objects out there which generate sort of these gravitational waves? The gravitational waves in this particular case that were detected were caused by the coalescence of 2 black holes in a binary system. Anyway, other things right over there. Just was reading 2 weeks ago that they might have found another particle at the Large Hadron Collider in Switzerland, and something that does not fit the Standard Model. So that's an interesting thing right there. Okay. Another thing is that there was a supernova just observed once again, just within the last 2 weeks. It's wonderful news, an exploding star. And then in January, studies indicated that there might be another planet out there in our solar system beyond the orbit of Neptune, beyond the orbit of our dwarf planet Pluto, far out there. They haven't seen it. There's no picture that they have of it, but based on how other objects in the solar system move, with perturbations, all these things, they surmise that there's got to be another planet probably somewhere out there, way out there. Let's see what happens. Other discoveries? Well, who knows dark matter in the next few years? We don't know. Remains to be seen. So, we are confronted by this immense, mind-boggling, and sobering universe. And this affects people in different ways. There's some for whom it's a very profound experience. For me, it's a profoundly religious experience. For others, it's a profoundly jarring experience. So some people out there, that religion is, it's a vast, cold universe, which is indifferent. I've had people tell me that, all that stuff. So people react to this reality in different ways. And the first principle that I'd like to talk about in terms of sort of this interplay between faith and science what are the principles around which this dialogue can be structured? What do you see most of the interaction? What is it in particular that allows our faith to really have a healthy relationship with the world of science? Well, I think the first one is just the basic questions that people ask. You look out into the universe, and it provokes a lot of questions very quickly. Okay. Well, what is it? How do things work? When, right? When did this universe in which we live originate from its original singularity? Where are things going? Where are other life forms out there? Right? They are. They're there. And of course, probably the most provocative question as well, why? And the most difficult. Why is there anything at all? What does it all mean? Where did it come from? Where is it going? What's my place in this reality? How is what I see all around me and so far away from me somehow connected to me? Is there a connection between my life and that which is around me? The big questions. The big questions because it's just natural to ask them. The big questions because our faith naturally lends itself to very existential questions. Questions of philosophy, questions of theological import as well. Those are two very common things that the world of science and that the world of faith have. The capacity to ask those big questions, perhaps with different priorities, but they're there. But very often overlapping. So they need to know. I mean, why do we ask? Because we want to know. We want to know. The human person seeks to know the reality about himself and herself, because in doing so, something of whom we are, we really become. Right? The capacity for thinking, for intellect. Something more of whom he is, knowing that his own life is bound up with the cosmos around him. Pope John Paul II, in his great work, Fides et Ratio, said this right over here, that's at the very beginning, the interplay between faith and reason. Faith and reason are like two wings on which the human spirit rises to the contemplation of the truth. And God has placed in the human heart a desire to know the truth, in a word, to know himself. So that by knowing and loving God, men and women may also come to the fullness of truth about themselves. The more human beings know reality on the world, the more they know themselves and their uniqueness. The question of the meaning of things and their very existence becoming ever more pressing. They are the questions which have their common source in the quest for meaning, which has always compelled the human heart like that. So we have this immense universe before us that provokes these questions. Questions in particular that cluster around a couple of things. Number one, what is the nature of the reality that we observe or in which we live in? The possibility of other universes, parallel universes, depending on the type of parallel universe theory that you have. Could you have universes out there in which there's an alternate you? Maybe an evil you, right? If you look at some of the Star Trek episodes, right? The evil spot. Where depending on what choice you made, gives rise to a different reality. So if your choice was cheesecake one day, between cheesecake and Oreos, if you chose the Oreos, how did your reality turn out because of that? Maybe the little white filling was poisoned and you died. So different realities, right? Something to think about. And if so, what does that mean for the issue of freedom, right? If there's a universe out there, an infinity of universes, each one dealing with a particular choice that you made, what does it mean to make a choice if there's a universe of your choice? That's a fun, mind-blowing question. And it definitely has its import for ourselves. Different universes, maybe with different laws and different constants, right? What might such life look like in a different universe? Then again, our universe, let's just stick to our universe instead of a multiverse. They say, string theory says that our universe might be 11-dimensional. We comprehend a three-dimensional universe, we know that there's at least 4 dimensions because of Einstein. But 11 dimensions, how do you make sense of that? So this diagram right over here is a representation of that. Each sphere right there tries to picture 2 dimensions bundled in a higher dimensional universe. These are just artistic drawings. I mean, these are not real diagrams right over here, just imaginations right over here. The nature of black holes. Once the light of an object or any information falls inside the point of no return around a black hole, the event horizon, you can never know what happens inside. What happens inside a black hole, in particular at the very center, which is known as the singularity, where our concepts of space and space-time break down. That's where time and space, as we understand them, have no meaning. What does that mean, right? Things like quantum teleportation, okay, which is just in its infancy. In other words, the transmitting of information from one location to another, which so far has only been done for atoms, very small tidbits of information. But could we ever have something, like what you see in Star Trek, being transported from one location to another? But then again, that's what happens, and what happens to a star, right? How do you disassemble someone and then reassemble that person at a different point? Space-time. Okay, there's a lot of people say that that's not possible. I think the one thing that it leads to is that there's very different domains of knowledge out there. It's clear that even in our physical universes, there's areas that we're just not privy to knowing everything about. Okay? So different domains of reality, each with its own method. Here I'm talking about the spiritual. I mean, how even in the physical realm, we already know that there are parts that we're not sure about their knowledge. What about the spiritual and the trail? Let me just put this on. There we go. So one thing where faith and science really have a healthy interplay is they concern themselves with 2 distinct domains of reality, each with its own method, each with its own realm of knowledge. And one always has to be very careful in clarifying these things when talking about issues of faith and science, because that's where a lot of confusion comes in. Another thing has to do with possibilities, okay? Beginnings and endings, creation and eschatology. It's natural when we're confronted by such a universe, especially one in which there's what we call a Big Bang, and possibly the end of the universe. What will the fate of the universe be? Will it expand forever? Will it contract in the opposite of the Big Bang into what's called the Big Crunch? Okay. Right now they say that the universe is expanding and that expansion is accelerating because of dark energy. And therefore, the fate of the universe likely seems to be that all the galaxies will eventually just recede from one another to the point to where you won't see anything anymore in the nighttime sky, and that ultimately the universe will meet a very cold death. Beginnings and ends. Beginnings, stars being born right over here in the Orion Nebula, and then stars at the end of their lives blowing themselves up right over here, the remnants of a supernova star that exploded long ago in the Crab Nebula. It's very natural for human beings to think about beginnings and ends. It's also natural to see that in the universe. We know that one day the universe as we know it will end. How? We don't know, but sort of the cycle of birth and death is something that lends itself very easily to a fruitful dialogue between faith and science. Eschatology, to use the words of religion, creation and eschatology. Okay, right over here. What role is there for hope, by the way, right? Another question provoked by the immensity of the universe is the obvious one. Are we alone? Are we the only ones? Or are there others out there? And all the issues that go with that. How is life defined? How is intelligent life defined? Statistics. It's a big universe out there. Does that mean, therefore, that it's full of life, right? Okay. Or are we the only ones? A highly improbable but possible outcome. What would such life be like in other places? The Kepler probe mission, just launched a couple of years ago, has discovered hundreds of planets in the local neighborhood. Okay. Some of which are very similar to the Earth in terms of mass, not necessarily continents and all these things. You have to be very careful when you hear twin Earth discovered in the news, because very often they're talking about a planet, very often the mass, or the same size as the Earth. It doesn't necessarily mean that there's oceans on it. Sometimes you see these artistic renditions and all that stuff. It might be, but then again, it might not be. So the possibility of life out there. It's sobering either way. It's sobering if we're just one of many, and it's sobering if we might be the only ones in this universe. Belief and extraterrestrial life. I think most people out there, most scientists probably believe that there is life out there. The probability is very high. But what kind of proof do we have? Actually, we have none. Okay? The most basic fact about this whole debate right now is that we have no idea. But that being said, I bet you could take a survey of most scientists out there, and they'd say that most of them do believe that it's out there. But you say, well, there's no shred of proof. Well, I have a hunch. I suspect. I believe. It's a very interesting conclusion. What about the interaction with faith? I mean, a lot of people think that somehow the possibility of extraterrestrial life out there somehow means the end of faith, of religion. People very often ask me that, and you can hear almost the concern under their question basically being, if they find that means our faith is doomed or something like that, that somehow it diminishes. And I go, no, not at all. Not at all. Not at all. Why? Ironically, our own faith, within its own system of beliefs, actually posits the existence of other rational creatures out there in this universe that God created. That's the irony. So certainly from a faith point of view, we're not alone. There are other intelligences out there that God has made. And therefore, for any person of belief, that possibility of finding extraterrestrial life, I don't think should be a threat. Now, of course, people very quickly go, well, Father, you know what I mean. I'm not talking about angels. I'm not talking about little green men. I go, okay, well, let's talk about that. But it's still a good way to really be able to deal with that debate. And if there are other physical, empirical beings in this universe, this known universe, I think that our faith is aptly positioned to be able to contribute to that dialogue. A dialogue which basically is this. I mean, it's going to be another Copernican moment for humanity. And basic questions of, well, once again, what is intelligence? What does it mean to be rational? Does being rational imply morality? How would you dialogue with a vastly different being, right? How would you dialogue with a being like that? I think that it's just as much a point of uncertainty for people who might not have any faith or different faiths as it is for people, let's say, of Christianity, who are confronted by this point. I mean, it is going to cause a massive shifting of how we look at many things, if and when we have that encounter with others out there. Interestingly enough, the Vatican actually held a conference on the possibility of extraterrestrial life in 2009. They invited a lot of prominent astronomers, chemists, biologists to the Pontifical Academy of Sciences for a few days to discuss from a scientific point of view. Well, what is science saying about the possibility of life out there? What do biologists say? What do chemists say? What do physicists say? What do astronomers say? They were just interested in just hearing the science and what scientists are saying, what science is saying. It was actually not held to craft a theological response. They just wanted to know, well, where are we at this? What do people think? I wasn't there, but I quickly got calls from the media asking for a comment about the conference, and I, of course, directed them to my boss, who was there. But as you can imagine, that generated a tremendous amount of interest. By the way, the USA Today coverage of that story, the headline was Pope and E.T. So anyway. Okay, a second principle, if we move on, is basically this: the reality and goodness of the created order. Another nice point of encounter between faith and science right over here. First of all, reality is good because it was made by God. That's what our faith teaches us for those of the Catholic Christian persuasion. The goodness of the created order. And therefore, the worthiness of doing science. Okay, we take that for granted. Okay? It is a good thing to do science. Okay? The universe is good, and therefore it is a worthy pursuit. God saw all that he had made, and it was very good. A second point is the incarnational, and very closely related to the first, is that material reality is not despised by God, but can bear the divine. Once again, the goodness of the created order. If the Word could take upon our flesh of this world, that means that this world is not corrupt. There are various sort of philosophies, various ways of thinking out there that either explicitly or implicitly regard this material universe as being bad in one way or another, or deceptive. But if from our point of view of the faith, even God assumed our flesh, then it is capable of bearing something of the divine, something of the truth, something of the good, something beautiful. It is not intrinsically evil, it is not intrinsically deceptive. There's no dualism between matter and spirit. And this goes a long way towards countering certain fundamentalisms. I had a person ask me a couple of years ago, especially about radiocarbon dating, basically saying, well, isn't it just the case that they've gotten it wrong, that it's a faulty method and all these things? And I go, well, you could always have a sample that's contaminated and therefore might give you a different result. But the science underlying it, assuming that everything is done as it should be done in terms of experiments, is sound. But not only that, that's the same science that contributes to you being able to have an MRI or a CAT scan when you go to the doctor and you have cancer. You can't pick and choose. Okay? You can't say, well, this is intentionally deceptive here, but then go to the doctor the next day, and the same technology, the same science is giving you an MRI that, ironically, you're taking the doctor's word for it. Okay? So once again, science is good. This material order is good. And very closely following upon that is that grace does not destroy, but rather builds on nature, perfects nature. Very often, I'm asked when I go to a conference, or just by people anywhere where they find out that I'm, in astrophysics, that I'm also a priest, they go, well, wait, hold on. Isn't that kind of impossible? I go, well, why? They go, well, the two just don't mix. In fact, they're at odds with each other. There's a conflict. It's like oil and water. Nonsense. They've always gone well, hand in hand. I've never, for myself, seen that. The order of grace, what is of the Spirit, because its truth comes from the same as that of science from God, complements and builds on nature. It does not destroy. Another major point right over here, the belief that something of the truth of God can be known from the book of nature, therefore. That somehow, from the point of view of faith, if you look at St. Paul, it says, from the book of nature, you can see the fingerprints of the divine. Certainly, as a people of faith, believe that. You see Psalm number 8, the heavens, when I see the stars, the moon at night, I think, what is man that you should care for him? Or Psalm 19, the heavens declare the glory of God, and the skies proclaim the work of his hands. These are writers of some of the books in the Bible. The basic belief that somehow in this reality of ours, something of the fingerprints of God from the point of view of faith can be discerned. Let me go on to the third point, and it's this. Nature is worth studying because creation is good, because grace builds on nature. Therefore, it is worth studying. Okay? It's a worthy pursuit. Science is a good thing. And hence, you have the pursuit of truth. Pursuit of truth, which is a very important thing, certainly in Catholic Christianity, and certainly the whole basis of science, the pursuit of truth about this universe, this common endeavor right over here. Divine authority not only does not forbid the investigation of reasons, of things visible and invisible, but it even encourages it. It is no small step, but then a great and indeed profitable one from the knowledge of the things we can touch to the understanding of the things we can understand in our mind. So it's Johannes Scotus Erigena, a monk, an Irish monk from the 8th century. Second thing is, therefore, the value of an education. People always ask, well, why is there a Vatican Observatory? And I go, well, one, most puzzlingly, is because there's always been one, or at least one for the last 500 years. Long before the controversies with Galileo and conflicts between faith and science in the 17th century. You saw that in the monasteries. You saw it especially with the birth of the university system, at least in the way that we know it, here in the West. The medieval universities like Cambridge and Oxford, Paris, Bologna, where astronomy was a discipline that was studied, the desire to know the universe around you, along with math, geometry, music, all these things. That somehow in studying this nature around us, this pursuit of truth, not only do we find truth, but it also forms us, once again. We ourselves are changed by the study of it. Okay. It's just not knowledge for a career, but the study of the material in itself is worth it, whether it's going to be used for something practical or not. There's a lot of people out there, well, I'll go to this school because I want to be trained well to get a good job. Well, those are good reasons, but the best reason for university is the study of these disciplines because they're good in themselves. They're good in themselves. The pursuit of the truth, and the truth does change you. It forms the person. And from the point of view of faith, it draws us closer to God. We exercise our capacity for rationality. Another assumption under this thing of worth study, the fundamental assumption that there's no contradiction between truths relating to nature and the truths relating to divine, that reason is common to both. Okay? It's really the intersection between science and religion. John Paul says right over here, from an address given to the Vatican Observatory, he says, science can purify religion from error and superstition. Religion can purify science from idolatry and false absolutes. Each can draw the other into a wider world, a world in which both can flourish. It's really a nice interplay between the two. Okay. Another big principle around which faith and science really have a wonderful, lively sort of interaction is over the whole question of intelligibility and rationality. Certainly from the point of view of faith that, and certainly from science that, when we look out into the universe, as I showed in those slides before, there's a profound order that we observe in this universe. These subatomic particles, these forces, and symmetries. Okay, the universe actually makes sense. Okay, otherwise, we wouldn't be able to do science. How would we find gravitational waves unless we were able to form theories and then try to go looking for them, right? I have a theory or I have a set of studies and I go, well, based on this and this and this, I suspect and I hypothesize that maybe this might be the case, and we go looking for it. And sometimes we find it. The universe made no sense. Would that be possible? Would it be possible to have laws? Laws upon which we can then build theories, and then from which we can learn something of this universe right over here. Is the universe finely tuned? That's a really hot topic on which there's a lot of disagreement. And that goes back to the multiverse. Okay. Is the universe and all the constants and all the laws that go into making it and give rise to life, and so far, us, we're the only ones, at least in our part of the universe, that we've seen. Is it fine-tuned, or is it just, if there's a multiverse out there, is it just the case that we're just one in an infinity of universes each universe with a different set of constants and laws like that. That's an open debate. It's a fun one to talk about. But certainly, we do see an order there. Can you conclude right away from this order that there's a creator in the sense of scientific proof? I don't think you can. Okay. Can you say, well, there's the grand designer? I go, well, not in the sense of a scientific proof and say QED. But can you look out there and see the order and the beauty of the universe and say, from the point of view of faith, I think that there is something there, from the point of view of faith. Why are there scientific laws? Another thing, we can make sense out of it. The universe makes sense, and the stunning thing is that we can make sense out of it, that there's something corresponding within us that is able to clue into something of what the universe is, its structure. Okay? All right. Number 3, under the intelligibility of the universe, the language of the cosmos, right? Especially in math. Very often when I open these, books that I use, books in physics and astronomy, and I open them up, and it's mostly math because I'm a theoretician. I approach astronomy from the theoretical point of view. I'm not an observer. I do observing once a year, but I'm mainly a theoretician, so I deal a lot with math. When I open a book and I see equations like this, it's a very profound experience for me. It's almost as if I'm seeing the language of God. That's my interpretation right there. These are known as Maxwell's equations from electromagnetic theory. I deal with these equations a lot. These are the equations of stellar structure. They tell you basically how a star will evolve. And putting in certain initial conditions and boundary conditions and all these things, it can give you how a star evolves using a good computer code. I spend a lot of time with computers. So right over here is the Schrodinger equation used in quantum mechanics a lot. But over here, an equation taken from relativity that basically connects the mass and the energy with the curvature in space-time that it causes right there. That's from Einstein's theory of relativity. And finally, moving just to the last two quickly, a very important part of the dialogue between faith and science is basically this. And a very fruitful part is both science and both faith seek to provide a comprehensive, coherent view of the reality that they perceive. Okay? It's a very big thing. So obviously in science, we see the world that astronomy has revealed, but we also, and in particular relativity, because relativity is the physics of the very large, okay, and very massive. And then we see the very small things in our cosmos, quarks, the Higgs boson, all these things. For that you need quantum mechanics. And the desire to bring those two things together to provide a coherent explanation of the universe, all the way from the very large to the very small. Right now there's a very big problem in the world of physics, and it's this, that we have theories that work wonderfully well for each domain, but it's proving very difficult to bring about a unified theory. This is a very, very hot pursuit in the world of physics to find a unified theory, or basically a theory of everything. Einstein tried, Hawking tried, and so far, nobody has succeeded yet. I suspect that somebody will one day. But to try to unite the world of quantum mechanics, the physics of the very small, with the physics of the very large, that still has not been done. But there's the belief that there should be a theory out there that should connect all these things to provide a coherent, consistent view of our reality. Okay? Right here, what Benedict says, faith consolidates, integrates, and enlightens the patrimony of truth that human reason acquires. Faith and reason can lead back to the conviction that both proceed from the one source of all truth, the divine Logos, which operates both in the realm of creation as well as that of redemption. It must be acknowledged that they make use of different cognitive procedures. So once again, if we throw the element of faith right in there, tossing into the debate, well, what is the even greater reality beyond even just our physical world? How do we integrate that just from the point of view of faith? Okay. That's one principle under comprehensive, consistent view of the cosmos. Number 2, interdisciplinary, that within their own fields, both faith and science try to, once again, have a consistency. How does cosmology talk to galaxy evolution? How does galaxy evolution talk to stellar evolution? How does stellar evolution talk to meteorites? There has to be a consistent picture. There should be a consistent picture. That's not always perfect, but that's a very important part. So when somebody in stellar evolution comes out with a theory, let's say that might have cosmological implications, the cosmologists very quickly say, well, let's look at that and see how we can integrate that right there. So what is said in stellar evolution, okay, has its use in cosmology. How do you mesh all those things together just within their own worlds like that? That's very important. Likewise, in the world of faith, biblical studies, systematic theology, dogmatic theology, morality, all these things, how do they mesh with one another? It's just not a bunch of separate camps that don't talk to one another. There has to be the attempt to unify, to be consistent across different fields. Another thing right over here is the interconnectedness of things and how it touches the human. In other words, so while we're talking about, well, how do all these things mesh together? How do they fit? Well, how do you bring the human into this, right? And I think certainly the faith is very good with regard to this. Where does the human being fit into all this? A huge universe and also a universe, okay, of great order on the microcosmic level. Well, where does the human being fit into this? Okay. I think that's certainly a big contribution that faith can make to the debate and interaction with the world of science. A place for the human dimension between the macro and micro, because we live in it. How does the view of the cosmos translate to human life? Issues of science, morality, justice. How does the universe that we see, that we understand, how does that relate to our notions of how science is done here on this planet, our morality, our system of justice, our politics, our economy, sociology, philosophy, theology? Basic questions. How do you explain origins and endings, the issue of freedom, the issue of suffering, love, suffering, life, death, beauty, the environment? How do they all fit in? Or in the end, is it just one patch here and one patch there and one patch there, and you really don't connect them in the end? No, certainly the world of faith seeks to unite those things into a coherent reality, consistent, logically reasonable, like that. So we can definitely make a contribution like that from the point of view of faith into the debates in science, because we live in a world that's bigger than science. Science is one slice, gives you an idea into one slice of our reality. Another principle right over here under just interconnectedness, a healthy, holistic, harmonious relationship between what's around us, and in particular, the environment. Okay, the last three popes, Pope John Paul II, Pope Benedict, and Pope Francis most recently, and certainly with great attention, have been very concerned with the environment. That we're part of a bigger world, and that the world affects us and we affect the world right over here. Okay, the Pope right over here, Pope Francis, interconnectedness of the environment, nature, and the social units within it, particular attention to the poor. Throwaway culture affects everything. Since everything is closely interrelated, today's problems call for a vision capable of taking into account every aspect of the global crisis. I suggest that now we consider some elements of an integral ecology, one which is clearly respects its human and social dimensions. It goes on to say, it cannot be emphasized enough how everything is interconnected. When we speak of the environment, we really mean is a relationship existing between nature and the society which lives in it. And we're faced not with two separate crises, one environmental and the other social, but rather with one complex crisis, which is both social and environmental. The solution to the problem that confronts us with regard to the environment and global warming is not just going to be solved scientifically, but with a greater reality that pays attention to the people around us, everybody to whom we're connected, issues of justice as well. I think that the faith is very well poised to contribute significantly to those debates right there. And in the end, it's just an extension of Catholic social teaching. So this is just a list of the basic hallmarks. And as you can see right over here, care for God's creation is right there as a concern among the U.S. Conference of Catholic Bishops, right over there. And on this side, stewardship, right? A proper interaction with the environment, as well as preferential option for the poor. Okay? So let me just end with this. Perspective. Why should we care about all this? Because as far as we know, we're the only ones in this part of our tiny part of the universe. It's probably replete with life. My own personal belief is that there probably is life out there. Okay? The chances are greater that there's life out there than there not being. But here we are, on this one little dot. By the way, that's the Martian sky. And that's how the Martians, if they exist, would view Earth, right there. So, right over here, come let us adore God the Creator. St. Ignatius says, to look how God dwells in creatures, in the elements giving them being, in the stars on this planet. Everything is interconnected. Right over here. That's one of our domes, and that's the little plaque right over there. Come let us adore God the Creator. That when we do this science of astronomy, we're taking the whole of creation into account. A sense of wonder, right? Ignatius. How do you connect the stars to what you do on the ground? Well, Ignatius just has wonderful words. St. Ignatius, the founder of the Jesuits. The greatest consolation he experienced was gazing at the sky and the stars, which he often did and for long, because thus he felt within himself a very great impulse to serve our Lord. Great connection between that which is around and that which is us. And then finally, the last thing. So the new rapprochement, is basically, in the end, for the most part, not new. It's a continuation of what's already been there for the longest time. You have so many great scientists from the point of view of faith. Copernicus, Galileo. Obviously, the great controversy with regard to Galileo over the issue of Copernicanism, which was not handled well by the church, admittedly. The mistakes were made. The important point also to make is that there are still men of faith who inaugurated great revolutions in the way that we saw the universe around us. Of course, you have Gregor Mendel with regard to biology and genetics. Father Angelo Secchi, a Jesuit, one of the founding fathers of astrophysics, came up with how stars are classified according to their light, that is spectra. And Father Georges Lemaitre, a priest from the Diocese of Louvain, who was the one who came up from the theoretical point of view of the concept of the Big Bang. And of course, Hubble with the empirical evidence right there. So, renewed in part because of new discoveries in physics and science that constantly prompt us, right? They're coming at us from every direction. An acknowledgement of the mistakes of the Galileo case has certainly contributed to a new relationship, right? Just to acknowledge it, just to say, yeah, it was a mistake. It was a very complex affair, no doubt about that. But the bottom line is still that a mistake was made there. And then renewed vigor on the part of the church, reappropriation and rehabilitation of past figures like Galileo, an emphasis on domains of competence. So much of the controversy back then with regard to Galileo was over how to interpret the scriptures. Okay, once again, proper domains of competence. The Bible is not a scientific book. Okay, it talks about truths with regard to God, but it's not a science textbook in the way that we conceive of one these days. Other factors, Pope Leo XIII refunding the Observatory, Pius XII coming out with a wonderful encyclical with regard to evolution. It's not really, has not been a problem in the Catholic world, certainly with other denominations, yes, much more problematic. John Paul II commenting on Galileo, evolution, fides et ratio. Pope Benedict, faith and reason, who was very strong with that. Pope Francis, obviously, with regard to the environment, has made a very significant contribution, which has been highly sought after by the world of science, okay, in support of how we face the great challenges facing our people, our planet, right? Anyway, so I think that's it right there. So thank you very much for your time. So if anybody has any quick questions, I'll certainly be happy to take any. You actually could have planets going around, let's say a binary star system, but they would have to be at an orbit that's far away, with a radius very far away from the two planets. In other words, in such a way that the orbit, how does one say it? That the orbit completely goes around the two. You couldn't, it would be very difficult to have a stable orbit with the planet going in between the two stars. So here you have the two stars, and let's say that you have a planet, let's say trying to trace a figure of 8, right, orbit. It would be very difficult to have a planet in a very stable orbit very close to the stars. But if you have a planet far enough away from the two binary stars, that you could have. Okay. And the Goldilocks, huh? Presumably, yeah. Presumably. But then again, the Goldilocks zone, once again, it's an interesting concept because right in the aftermath of that conference on extraterrestrials, the possibility of extraterrestrials that the Vatican sponsored in 2009, we had one of the astrobiologists, okay, that is a field in the realm of astrophysics along with cosmology. There are astrobiologists. Of course, the irony with this is that usually you need data points to have a good science. And in this case, there is no data point. In other words, it's a completely speculative field. But why not do it? So we had somebody, I mean, he's really an astronomer, but he calls himself an astrobiologist, very well respected, and he came and gave us a lecture at the observatory on if there is life out there, what types of planets and stars would it exist in? And his conclusion was that the types of stars around which you would find planets on which there could be life would be stars less massive than the sun, therefore cooler, and at an orbit much longer. In other words, these would be very cold worlds. Cold worlds harboring a type of life that is radically unlike anything that we can conceive. So the Goldilocks zone is, in a sense, a bit anthropomorphic. In other words, life as we know it, right? Life is as we know it, because so far the only data point that we have with regard to life is just that which you find here on Earth, right? But you've got to start with something, right? So a lot of what the Goldilocks zone is about is basically, well, life as we know it, if it were to exist, take a certain zone of habitability, right? Just picture sort of an annulus, an annular ring around the sun or star, and a planet falling somewhere within that zone, like the Earth, where conditions would be favorable for having life on a planet. Well, in this case, the Goldilocks zone for such solar systems would actually be very different and would harbor, life that is unlike anything we know. For example, oceans that would not be water would be other types of chemicals, such as a methane ocean, liquid methane, or some other type of hydrocarbon ocean like that. And what would life arising in such an ocean be, right? And cold. Where would it draw its energy from? From the heat of the planet as opposed to the star, right? Would it be hot enough outside? This is an interesting thing where, once again, going back to one of the first principles that I mentioned, in other words, how do you frame the discussion? Because it's very common to say that the Big Bang Theory, it's very common for a lot of people in the world of faith to say, well, the Big Bang faith is obvious evidence that God exists, that God is the one who caused it and all that stuff. Because there would have been nothing before that, presumably, but we don't know that. We don't know that. Did this universe result as the result of another universe that had previously collapsed? Is it a cycle of universes, or is it one of a multiverse, physically speaking, and all these things? So all that we know from the Big Bang, all that scientifically, from the scientific point of view, is that the universe 13.7 billion years ago, the totality of it, would have been in this incredibly dense point, this singularity, which then blew itself apart, and from which the universe, as we know it, has been expanding since then, 13.7 billion years ago. Was there nothing before that singularity, scientifically speaking? Well, we don't know, like that. So, once again, from a scientific point of view, you can't say, well, this is obvious proof that, therefore, you have this first cause which snapped its fingers and suddenly the singularity popped up and the universe came into existence. And most you can say, well, the singularity was there and it blew up into what we know. And certainly from the point of view of faith, at some point, regardless of whether there's a multiverse or there was just our universe that just expanded into existence, at some point you say, well, of course, God is the one who brought it into existence somehow. But you cannot, from just the scientific evidence that we have right now, the scientific observations that we have, say, well, from this, it's clear that suddenly some other power caused this to be. The space between spaces, actually this would be one way of looking at it. Actually, there would be no space between spaces, because space itself is a characteristic of our universe. In other words, our universe is defined by space-time. Space and time are qualities that define our universe. So for example, let me just go to a different example, but something that's very similar. It's very common for people to ask, well, what's the universe expanding into? As if there's a bigger room, right? And that somehow the universe, like a balloon, is expanding the room and taking up more and more space. And the answer is, well, actually, there is no space outside of space, because what we define as space, as we know it, is defined by our universe. Is there a beyond? Yes, but it just wouldn't be what we would identify as space. What would there be between universes? I don't know. The bottom line is I don't know, but it's not space in the way that we conceive, as if you have multiple bubbles. Keep in mind that some of these diagrams are just conceptions, because we have to go on something that we do know, right? So there would be beyond. There is a beyond space. There is a beyond time. So for example, time exists in this universe, but outside of this universe, there is no time. There is a beyond. So when we say, for example, let me switch over to faith. When we say that God is eternal, it doesn't mean that God has always been living in the sense of ordering his life according to some big God clock. It means that God is outside of time. When you say that God is eternal, it means that God is not bound by time. God is beyond time. In fact, God makes time. Now going back to what you asked, just keep those things in mind, that when we refer to issues of space and time very often, it's concepts that apply only to our universe as we know it. What lies outside, all we can say is, well, something beyond, some possibly other universe. Once again, opinion is very much divided on the possibility of a multiverse. Okay. In fact, a lot of scientists basically would say that they really don't hold out the possibility of something like that. For one thing, there is almost a contradiction with its having been proposed, and it's this, that you have no way of ever being able to verify that it actually exists. Which, of course, in the world of science, you need some empirical verification sooner or later, right, to go on. But it's a theory that in the end, ironically, originated within the world of science, that has no possibility, as far as we know, but that could change, that could be verified. That being said, a couple of months ago, there was a report that I saw in which there is a physicist who claims that he's been able to calculate and is looking for evidence of actually the collision of one universe with ours, like that somehow you could detect, according to him. So the interaction between universes, you couldn't see into the other one, but apparently the interaction between another universe and ours, he claims that you could detect. I don't know the details of that, but stay tuned and see. Just the fact that we're able to describe all these things, that we're able to form theories out of them. So as a case in point, I spend a lot of my time in front of a computer. I do a lot of computer simulations. My job is to take the data that's collected by the observers, the ones who use the scopes, and then to try to make sense out of what the data tells you by building up a theory. And usually that's done on a computer, because usually you're dealing with clusters of a lot of stars, 1 million stars at a time, or a couple of thousand at a time if you're dealing with an open cluster. So you cannot sit there and count one by one and its temperature, these other properties. You have to use a computer. But the fact that you can actually write a program, put these equations in there in numerical form, and actually come out with something that is able to give you a simulation of the way that something works, or is thought to work in many cases, for me, just blows my mind. And as I'm making assumptions in the program, because keep in mind that not everything is figured out 100% in the world of science. A lot of the things that I'm writing into the program or into the theories are assumptions. For example, the sun. Okay, you have to assume, to make things easy, that the sun is a sphere, a perfect sphere. The sun's actually not a perfect sphere. It's actually a bit flattened because of its rotation. Okay? But the math to handle that kind of a structure is very complicated. And so what you do, you just say, well, let's just assume that the sun is a sphere. And that's done to good approximation, actually. It does work. And so that's one assumption already. And there's just assumption after assumption after assumption that you make, and you're going on a hunch, a reasonable hunch, okay? It's just not a wild guess, but you're sitting there, there's good reason to think that I can make this guess right over here, this assumption here. And it still works. One assumption that has to do with gravitational radiation is this. One of the ways in which these stars that I study form, these helium-burning stars, right? These midlife crisis stars that burn helium. Stars, young stars like the sun, burn hydrogen in their centers, okay? For billions of years, at least the low-mass stars. And as they burn their hydrogen in their center, not in the outer parts, but in the center, in their cores, the result of those nuclear reactions, fusion, okay, is the energy, of course, that's radiated by the star in helium. So as time goes on, after a couple of billion years, you have a big helium ball at the center of the star. And helium is a lot harder to fuse than hydrogen. And that's when the star becomes a red giant. And then through a lot of interactions, through a lot of processes, basically the core gets squeezed again by gravity and to a temperature high enough to ignite the helium, and you get this helium-burning star. And once again, these helium-burning stars, these very hot stars, the big question about them is, how did they lose most of their outer envelopes? How did they get stripped of most of what they have just to leave this basic helium ball? Another possibility is that, once again, in a binary system, two white dwarf stars, these are stars, low-mass stars that have already come to the end of their lives, basically orbit around one another, and their orbits decay until they finally coalesce, and the interaction gives you that helium-burning star. The orbital decay of those two stars in the binary system happens. How does the energy get dissipated? Ironically, through gravitational radiation, gravitational waves. So even my work did get affected by this discovery because it carries with it the assumption, okay, these two stars will ultimately coalesce because of the loss of gravitational radiation through these waves. Now, once again, that's not my main field of work, relativity, but you just assumed it. And so I was happy to say a couple of weeks ago, well, actually they do exist. Good, that was a good assumption. Okay? So it's things like this. Actually sit there and just having the computer program in front of me, so I'm going through it, and the fact that you can describe all these things through these instruments is a very profound experience for me, like that. Okay. If you just stick within the realm of faith for a second, you would say that something happened in this part of the universe that somehow affects a different part of the universe without lessening the others. I suppose you could use the comparison that the incarnation happened in one spot on this earth as opposed to other locations on the planet without the denigration of other peoples on the planet, right? Other nations, other cultures, and all that stuff. So you could take that, you could look at it from that angle. There's one possibility as well. But, these are highly speculative things. This is exactly the things that we should be speculating about and thinking about in terms of thinking about the possibility of, well, how would we handle other life in other parts? And what belief systems would they have? Would they have any? Okay. Would they have, how would they do science? Even basic issues like that, right? What kind of equations would they have? Like that. So it cuts across the whole thing. Okay. Anyway, I better stop because I've gotten the signal that it's time to let you go. So thank you very much.